Section 2.4.3 Force damped oscillation.
Right. So, force damped oscillation, this is where the fun begins. So this time we've got the same thing, a mass spring damper system. Obviously I've got a displacement of x, okay, and I've got a force that's being applied, F of t. Okay. Mass spring damper system, I've moved it back x, but there's a force that's being applied as well, F of t. And then again, we're going to apply a sinusoidal force. We'll talk a little bit more about these different forces in chapter 3, but let's take a sinusoidal force. So again, Newton's second law, mass times acceleration is the sum of all the forces. So we've got the spring force minus kx, we've got the damping force minus cx dot, and we've got our force that's being applied, F naught cosine omega t. Now again, omega is not the natural frequency, it's not the damped natural frequency, it is the driving frequency. It's the frequency I'm giving to the system. F naught is the amplitude of that frequency. So we can make our substitutions, C upon m and k upon m, so we end up with this, and we're moving to the complex plane again. So we're replacing x with z, complex number. And because we're using a complex number, we can try a trial function. We know that the system's going to oscillate. Notice I've changed the cosine omega t to ej omega t, because we know that that's an oscillation. Okay, we're going to try a trial function, and we're going to predict that the frequency of that trial function will be omega, because it's going to end up going at that frequency anyway. Okay, we've got a phase in here which is delta. We'll worry about that in a minute, and we've got a certain amplitude. We don't know what that is yet. So we'll stick that in for z and see what happens. So we stick that in for z. We end up with a minus omega squared plus j gamma j omega plus omega naught squared. Okay, e j omega t minus delta, and that's f naught upon m e j omega t. Okay, because remember we took this equation, this one here, and divide by m, you get f naught upon m over here. Okay, so we make that substitution. We move into now the e j omega t terms, they'll cancel out. Okay, so on one side we've got e j omega t, because remember what you've got when you've got a sum up here, you've got e j omega t times by e to the minus delta. Okay, it's the same thing. And so ej omega t and ej omega t, they disappear, okay? And so we end up with this equation, and this was e to the j times by minus delta. Well, obviously, if you divide by it, it becomes e to the j delta, which is why it's over here, okay? Still in the complex plane, we could rewrite the right-hand side over here. So all I've done is I've taken that term. We know that's a complex number, so that's in there. Yeah? Does that make sense? And the real and complex parts must be equated to each other. Okay, so the real bits must be equal to f naught upon m times by cosine delta, and the complex parts must be equal to sine delta. And so we can do that. Okay, so you end up with this equation. So there's our real bits. We've got a minus omega squared and a plus omega naught squared times by the amplitude A must equal f naught upon m times by cosine of delta. And then the complex bit in this equation, we've got gamma j omega, okay, times by A must equal f naught upon m times by j sine delta. Or the j's disappear, we end up with that, the imaginary bit, with that bit, which is an imaginary bit. They must be equated. Remember, this is where we had the problem where, back in the free oscillation, there was no force, so this bit on this side was 0, and obviously that couldn't be 0. Okay, so that would mean the amplitude is 0 and the frequency was 0, and the gamma was 0, which is, just doesn't make sense. Two equations, two unknowns. Okay, A and delta are the things we don't know, and you can do the maths. I won't bore you with the arithmetic, but that's what it comes out. A comes out to be that, and delta comes out to be that. Okay, so we end up with two equations. Now, they're in your notes. If you look on pages 30 and 31, you can see those two equations. And obviously, you can return to the real world. We know what A is, and we know what delta is. Okay, they're defined there. So that is the equation for a forced oscillation system. Okay, with damping. And again, that A cosine omega t minus delta, that's almost equivalent 100% with the case where you've got no damping. Okay. Again, the system will oscillate at the frequency at which you're driving it. Okay. The system will oscillate, like I said, it doesn't matter what it wants to do. You're driving it at a certain frequency. If you're strong enough, it will go at that frequency. Okay. Now, again, A is not adjustable. It's dependent upon your system and the forces being applied, as is the phase. Okay. So again, like the force system with the free oscillation, it doesn't matter what happens to start with. A will be determined entirely by your system. So you've got F, which is your frequency. You've got your mass, which is obviously the mass of damping. The natural frequency system, which is related to the mass and the stiffness of the spring. That's the frequency you're driving it, so you know it. And gamma, which is C upon M, and you know what C is because, again, that's a characteristic of the system. A is completely reliant on the system. Okay? And the same thing with delta. Okay? Delta's just got omegas and gammas in, and you know all those things. They're related to the system and the force at which you're applying to the system. So they are no longer adjustable. Okay? So with the free oscillation, basically free oscillation, A and your phase, okay, will be dependent upon initial conditions. What happens when you start the oscillation off? The same with damping, with damped and with undamped. Okay, you will define those based on initial conditions. If there is a forcing function in the system, as if you're forcing it with a frequency, okay, frequency that you decide, and with an amplitude you decide, the system will therefore respond in a way that's completely defined by the characteristics of the system and the force you're giving it. Okay, it's no longer reliant on initial conditions. It doesn't matter what the system is doing and when time is zero. Okay, you will give it a forcing function, and the system will respond. And eventually, when all the transients die away, you'll end up with this situation where you've got an oscillation with a certain amplitude dependent upon the system and a certain phase dependent upon the system. Constants A and delta are not adjustable anymore. And they're defined by the characteristics of the system and the characteristics of the applied force. Now we can look at what happens. There's our equation for A. Okay. Let's look at what happens when we have different values of omega. This is the driving frequency, so we can choose that whatever we want it to be. Omega naught is set by whatever we've got our system set at, in terms of the mass and the stiffness of the spring. Okay, but omega we can choose. Omega without the subject, we can choose whatever we want that to be. We can drive the system at very low frequency, or we can drive it with very high frequency, or we can try and drive it around the natural frequency and see what happens. And what we can do is we can stick in different values for omega and then plot the results. And we'll see in this minute the plot, but basically, as omega goes to 0, we end up with F0 upon K. That makes sense. That's a static displacement. If you're not oscillating the system, you pull it back, the force with a force, okay? The force is just going to be being opposed by the spring, yeah? And the spring is the spring force is K times the displacement, okay? A is the displacement, time multiply that, okay, you get a force, okay? So that's static displacement. That doesn't change. And that's what happens if you stick an omega naught into this equation. Sorry, omega equals naught into this equation. That term disappears completely. That term disappears. We end up with F naught upon M
divided by omega naught to the power of 4, which is omega naught squared.
And obviously, if you do the maths, you end up the m's cancel. You end up with F naught divided by K. Okay, that's what happens there. And like I said, that's called static displacement. What about delta? Well, delta is there. If we set omega to be 0, okay, then obviously it's a inverse tangent of 0. Okay, an inverse tangent of 0 is also 0. Okay, because tangent at 0, tangent is also 0. Okay. So if omega naught, delta is 0. Now what about if we're driving it at the resonant frequency? Well, if omega and omega is almost equal to omega 0, if we go back to our equation for A, if those two terms are equal to each other, okay, then obviously that term becomes 0, yeah, and that term becomes omega naught, because that's what we're driving at that frequency, okay. So you can put the values in, you end up with this term, f naught upon k times by a constant that's dependent upon the system, okay. Omega naught is root k upon m, and gamma is c upon m, okay, so we can basically, you've got, if you remember when we're with a undamped system, and the A went to infinity, didn't it? Okay. We can see that in this case, with damping, it doesn't go to infinity. It goes up by a certain amount, and that value we call Q, which is the quality of oscillation. Now, we call that quality, basically, if the system's good at oscillating, so the damping is low, then it's got a good quality of oscillation. You can see that makes sense. Okay. If damping is low, then Q is going to be high. And if damping is high, it's on the denominator, then Q will be low. It's a poor quality oscillator. So think about Q as being quality of oscillation. And so you can say that the amplitude, when you've got omega approaching your natural frequency, is going to be some factor multiplied by your static displacement. Okay, some factor multiplied by the static displacement, and that factor Q is dependent upon your system. And then, in the case where the driving frequency approaches infinity, our A equation will end up being upon infinity, f naught divided by m divided by infinity, and obviously that's approaching 0. So again, the same situation happens. You start off when omega is very low at your static displacement, and then as omega goes to infinity, okay, your displacement goes down to 0. Okay, as your frequency gets higher and higher and higher, the amplitude of oscillation will reduce. But around the natural frequency, it's going to increase by a certain value, and that value, instead of being it going to infinity like it did with the undamped case, because there's damping, it doesn't go to infinity, it goes to a peak. And that peak will depend upon the damping in the system. It's less obvious what happens to delta in these two cases, and let's just say that this is what happens. At omega, so delta is the phase. At omega equals omega naught, okay, the system will respond 90 degrees out of phase with what the force you're giving it, okay? So if I'm applying a force this way, it's going to wait 90 degrees of the cycle, and then it will respond as well. So you get this sort of situation like this, okay? So the system will be delayed in its response. As omega goes up and keeps going up, you end up getting the situation where you're 180 degrees out of phase, okay? Pi radians is 180 degrees, where if you're forcing like this way, it's actually moving this way, so you get this sort of situation. So you start off, very low frequency, it does this, okay? And slowly, as you increase the frequency, okay, you get a delay in the response, okay? And then as you go further and further and further, you get it being completely out of phase with each other, okay? You see that in control as well, when you talk about frequency domain stuff. So this is what it looks like. There's A, okay? Start off at omega equals 0, okay? You've got f naught upon k, static displacement. As you increase your frequency to omega naught, okay, the amplitude is going to go up. And it depends on your damping. With very high damping, it doesn't go up by much. With very low damping, it goes up quite a lot. And like I said, with zero damping, it goes up to infinity, doesn't it? Yeah? So it goes up to infinity. So with f naught upon k, it goes up to a certain point, and then will fall back down to 0 as you increase your frequency. And your delta, if we plotted the same thing with delta, at 0 frequency, okay, there's no phase. It's going to respond in the same way that you're applying the force. Okay, as you increase your frequency to this point, you're going to be a bit behind, okay? And then as you go beyond it, it becomes more and more like a completely opposite. And again, the speed with which it goes from 0 to 180 out of phase is dependent upon your damping. If your damping is very high, very high, which is this line, it takes a long time. If your damping is very low, okay, then obviously the speed changes quite quickly. Now you'll notice, if we look at this thing, the peak of the amplitude, so this bit here, there, and there, notice that it happens slightly before your natural frequency. And that depends upon the damping, okay? And then the less damping you have, the more likely it is actually at the natural frequency. But that peak doesn't actually occur at the natural frequency. And there are equations that will help you define that. So the frequency at which the maximum does occur, okay, which is here, A max, is equal to this. And you can see that that depends upon Q. Q is omega naught upon gamma, so Q, okay, the quality of oscillation. So you've got an equation there that's dependent upon the natural frequency of the system and the damping that's in there. If damping is very low, then Q is big, and you end up with the square root of 1. Okay, 1 over something that's huge is 0. Okay, so you end up with the bit being at the natural frequency. If Q is very low, so damping is high, okay, then obviously this number comes into play and it reduces the value of omega naught, or reduces the, this number becomes a number that's less than 1 times by omega naught. The maximum amplitude actually is slightly different to what it is when you've got, well, obviously what we've done here is we've stuck in our omega into that frequency, okay, and that's what the end of what you're getting there. So by way of example, if Q is 5, so very underdamped, equivalent to a damping ratio, we'll cover damping ratio next week, okay, but damping ratio 0.1, then omega max is 0.99, so it's 0.99% of omega naught, so it's 1% lower, okay, and A max is F naught upon K, so it's 5.03, so it's only 0.6% higher than Q. So it doesn't actually make that much difference with a very underdamped system, whether you take these equations or those equations, okay, for the frequency.